we're going to explain this again, what causes a greater response, in just a few minutes. If we were to continue to increase the strength of the stimulus, we would get an even greater response in a positive direction, but it would take longer to return back to resting levels. Increase the strength, we get an even bigger response toward the positive level, and it takes even longer. Step by step, in proportion to the strength of the stimulus. However, if we could stimulate the inside, the neuron, hard enough to reach this certain point called the threshold. The threshold is a boundary, and I think I tried to make this point before. Where the door is a threshold. You cross that threshold, you hit something entirely different out there in the hallway. You come to this side of that threshold, you get this laboratory. That's different from the other side of it. And so a threshold is a boundary. And in this case, if you can stimulate the inside of the neuron from rest enough to reach the threshold, then you no longer get this pattern of response called a graded response. Instead, the electrical changes that will happen would look like this. The inside continues to get more and more positive, or less and less negative, however you look at it, up to a certain point, always up to a specific level. Okay, and then the electrical response will return back to resting levels, but typically it gets a little more negative than resting levels, and then returns back to resting levels. This type of electrical response is no longer called a step-by-step graded response. What do we call this electrical response? An action potential. Okay, so to add to another bit of information, any of these chemically gated channels can only produce graded potentials. So you only get graded potentials anywhere on the nerve cell body or on dendrites. You could get both positive graded potentials from all of the excitatory neurons that are trying to influence our neuron of interest. All right. The more excitatory presynaptic neurons that are firing on this neuron of interest at the same time, then the more their stimulus will add together and make the inside become even more positive, the more of them that add together. Question?
So the graded, they don't transmit signals
No.
because they can only reach that threshold?
Exactly.
Oh.
You got it. Nailed it on the head. Okay. So the function of the graded potentials is to add up enough to reach the threshold. Okay? Because the graded potentials are coming from individual neurons that are trying to influence our neuron of interest. They're trying to make this neuron fire. And the way that this neuron will fire is if we can make the first action potential occur at the very beginning of the axon. This very beginning of the axon is called the axon hillock. It doesn't look any different. It's just the area of lowest resistance. It's the easiest place for an action potential to get started. Okay? And what all of the other presynaptic neurons are trying to do, each individual neuron doesn't have enough power by itself to make the postsynaptic neuron, our neuron of interest, reach its threshold. And so it will take the effects of many neurons adding their effects together in order to try to collectively get the postsynaptic neuron to reach threshold for an action potential. Once the first action potential is created, then that's going to cause the next part of the membrane to create an action potential. And then the next one, and the next one. And it's like tipping over dominoes. The spread of the action potentials down the axon is what constitutes the spread of the electrical part of a nerve impulse, all the way down to the tip of the axon. Okay? So, one other point. The distance that these spreading action potentials reach will not vary. In other words, you get the same strength of the signal no matter how long the axons are. Imagine in the longest nerve called the sciatic nerve, you got some individual nerve cell axons that reach from the base of your spine down to your foot. That's a microscopic, small diameter cell that's almost 3 feet long. That's an awful long way for a signal to travel. And by this method, by the spreading of axons, the signal is just as strong if it has to travel 3 feet, or if it has to travel 9 feet in a giraffe. The signal is just as strong from start to finish when it arrives, because it's the spread of action potentials that constitutes the spread of the electrical signal. All right? Yeah, I will have to say this a couple of times for it to sink in, because you're not used to, it's a lot of stuff to take in the beginning, but it will come together. Okay, so let me give you the overall picture again, and then we'll look at the details, and then you'll see how it all fits together. So in reality, the way that this works